This is section 8.4 in your book. It's on comparisons of series. There are two comparison tests that we're going to take a look at in today's lesson. The first one's called the direct comparison test. We are going to directly compare two different series. If we know something about one series, then we hopefully can say something about another series. So first thing we need to happen is we need to have two series where one of the series is always bigger than the other one. So first of all, they both need to be positive. They both need to be greater than 0. And the series B, every term in series B has to be greater than, or it could be equal to, every number in series A. So B is always greater than or equal to A. And then we can say if the sum of sequence B converges, then the sum of sequence A also has to converge. Basically, if the bigger sequence, if its series, if I add up all the terms to the bigger sequence, if that converges, then something that is smaller than that also needs to converge. Basically, if we think about it this way, if I have like 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. Whoops, 1 over 16, not just 16. Plus 1 over 25. And we know this converges. If you have something that's smaller than this, so maybe like 1 over 2 plus 1 over 5 plus 1 over 10 plus 1 over 17 plus 1 over 26. So adding all these up converges to something, and all these terms are all smaller than those. Therefore, this one also has to converge because everything in here is smaller than this. So like if this equals a number, then this has to equal a smaller number. So if the bigger sequence, if the sum of the bigger sequence converges, then the sum of the smaller sequence also needs to converge. And then if the smaller sequence, if the sum of those terms diverge, then the bigger sequence also has to diverge for kind of the same reason. If all the terms in this are bigger, and when I add these up, it gets me something that goes to infinity, then this one also has to diverge. So if the bigger sequence converges, then the smaller one also needs to converge. Or if the smaller one diverges, then the bigger one also has to diverge. So let's take a look at one of these. We are asked to determine the convergence or divergence of this sequence. 5 over 3 plus 4 to the n. The sum as n starts at 1 and goes to infinity of 5 over 3 plus 4 to the n. And we are going to check for convergence or divergence by comparing it to the sum as n goes from 1 to infinity of 5 over, we're going to take out that 3 plus, 5 over 4 to the n, which notice is the same thing as the sum from 1 to infinity of 5 times, the 4's on the bottom, so 1/4 to the n. So this sequence here, if I start plugging things in, if I plug in 1, I get 5 over 7. If I plug in 2, I get 5 over 19. Plugging in 3, 4 to the third is 64 plus 3. Plugging the same numbers into this one, I've got 5 over 4 plus 5 over 16 plus 5 over 64. Notice the denominators on this one are bigger than the denominators on this one. I'm dividing by a bigger number. All the terms in this sequence are going to be smaller, which makes sense because I'm adding 3 to the bottom. So if I add 3 to the bottom, my denominator in this sequence is always going to be bigger. So this sequence, every term in this sequence is smaller than every term in this sequence. We also know that this is a geometric sequence, a geometric series, because we're adding them up. This is geometric with an R value of 1/4, which is less than 1. Therefore, this converges. Therefore, something that every term is smaller than that also must converge. Let's try another one here. This one says the sum as n starts at 3 and goes to infinity. It starts at 3 because if I plug in 1, I get a negative number, which notice it said that everything has to be positive. Also, if I plug in 2, I get undefined, which is no good. But starting at 3, if I plug in 3, 4, 5, and so on, I do get all positive numbers. We are going to compare that to the sum as n starts at 3 and goes to infinity of 1 over n. 1 over n to the first. This is a p-series. It is a divergent p-series because p is 1. Any p-values less than or equal to 1, p-series diverge. This one here, we are subtracting 2 from n, so if I'm subtracting 2 from the denominator, this is going to have a smaller denominator, which if I divide by a smaller number, that's going to give me a bigger number. So we can say 1 over n minus 2 is greater than or equal to 1 over n for all n greater than or equal to 3. Therefore, these two series do the same thing. This diverges. This is always bigger, therefore this also diverges. The direct comparison test, usually you're not given one like this where you have to, where it simply asks for the convergence or divergence, because there's actually an easier way, which we're getting ready to talk about, on how to do one like this. But there are multiple choice questions where you need to understand how the direct comparison test works. We'll take a look at some multiple choice questions starting next class. The more useful of the two tests is called the limit comparison test. The limit comparison test says that we have two positive sequences. And what we're going to do is we're going to take the limit as n approaches infinity of a sub n over b sub n. We are going to divide the two sequences and evaluate the limit as n approaches infinity. If that gives me a finite positive number, then the two series do the same thing. Either they both converge or they both diverge. So if we know something about one of the series, and I divide the two, evaluate the limit as n approaches infinity, I get a finite positive number. That tells me something about the other series. Usually we'll be given one of these, and we'll try to come up with something else that when I divide it, it gives us a finite positive number. We'll take a look at how to do that. So this one asks us to determine the convergence or divergence of the sum as n starts at 10 and goes to infinity. Again, it's starting at 10, so that when I plug in 10, 11, 12, 13, and so on, I'm getting all positive numbers here. Of 4 over root n minus 3. To figure out what we're going to compare that to, you are going to take the highest power of n in the numerator and the highest power of n in the denominator. So I don't have any n's on the top, so I'm going to go with 1 on the top. And on the bottom, the highest power of n is root n. So this is what we are going to compare it to. Notice both of these sequences, if I start plugging in 10 on up, I get all positive numbers. So it does meet that criteria. Now we are going to evaluate the limit as n approaches infinity of the ratio of the two. And it doesn't matter which one you put on top and which one you put on bottom. So I'm going to take this divided by that. So I'm evaluating the limit as n approaches infinity of 4 over root n minus 3 divided by this. Dividing by that's the same as multiplying by its reciprocal. To evaluate the limit as n approaches infinity, we check the degree on the top, it's 1/2, and the degree on the bottom, it's also 1/2. If those are equal, we divide the leading coefficients, which is 4 divided by 1. This limit is 4. That is indeed a finite positive number. Therefore, these two series do the same thing. They either both converge or both diverge. This one here is a p-series. Our p-value is less than 1. Therefore, this diverges. So we can say that this over here also diverges. Let's try another one here. Again, I have everything where it's n to an exponent on the top and the bottom. We're trying to find the convergence or divergence of that really gross thing. Again, we're going to use the limit comparison test. Notice anything else you try to do, it's not geometric, it's not going to be telescoping. Nothing else we've talked about. It's not a p-series. We could try to evaluate the limit as n goes to infinity. That would give us 4 over 5. 4 over, not 4 over 5, I'm sorry. It's going to give us 0. The highest power is on the bottom here. So we cannot say it diverges simply based on that. So what we're going to do is we're going to compare it. We're going to take the highest power of n on the top, end of the third. Highest power of n on the bottom, end of the sixth. Divide them. Gives me 1 over n cubed. That's what we're going to compare it to. If we're comparing it to this, what we do is we evaluate the limit as n approaches infinity of this guy here. Divided by this guy here. Again, dividing is going to move it up to the top. You can distribute this, although I'm just going to think through the distributing. If we're evaluating the limit as n approaches infinity, if I distribute this, the highest power of n on the top is 6. On the bottom is 6. So we divide the leading coefficients, which is 4 over 5. Because this is a finite positive number, I know these two series do the same thing. This is a p-series. Our p-value is greater than 1, therefore it converges. So this also converges. One more here. We've got the sum as n starts at 1 and goes to infinity of n squared times 3 to the n over 5n to the 4th plus 1. N squared times 3 to the n over 5n to the 4th plus 1. In order to find what we're going to compare that to, we're going to take the n squared here, like we usually do. This 3 to the n, we're just going to leave it where it is. We do want that 3 to the n in there. N to the 4th is the highest power of n on the bottom. So we are going to use 3 to the n over n squared as our comparison. So again, if there's an exponential part in there, you're going to want to leave that part in. Anything else, if there's like a plus 72 on there, anything like that, you can disregard that. So again, it's the highest power event if there is an exponential, or if there's a factorial. We'll look at something like that eventually. You're going to want to leave that stuff in there. So we are evaluating the limit as n approaches infinity of one term, which is n squared times 3 to the n over 5n to the fourth plus 1, divided by this. If I divide by that, I'm going to flip it. These guys cancel. I've got n to the fourth on top, and the highest power of n on the bottom is 4. Divide the leading coefficients, gives me 1 over 5, which is a positive finite number. These two do the same thing. This one here, it's not a p-series. Part of it is, but the whole thing's not. It's not geometric. Part of it is, but the whole thing's not. We can evaluate the limit as n approaches infinity of this guy. 3 to the n over n squared. If you plug in infinity, you get infinity over infinity. So you can use L'Hopital's rule. Derivative of 3 to the n is 3 to the n times ln of 3. We still have infinity over infinity, so we have to use L'Hopital's rule again. So derivative of 3 to the n is 3 to the n times ln of 3. So now I have 2 ln of 3's. If I plug in infinity, I get infinity on the top and 2 on the bottom. So this diverges. We have shown that the two series do the same thing. Therefore, this one also diverges.